Hey everybody, and welcome back to Linear Algebra Online. So today is the start of a very important unit in linear algebra. It's kind of the one where we really pull everything we've learned together and see, actually for the first time, why this stuff is so useful. And it's kind of summed up really well actually in the book right here. So the author says that this is the real power of algebra, its ability to take properties from a concrete setting like Rn, which basically this is what we've been studying, right? And then abstract them to a general setting. So the idea with this unit is basically that I'm going to show you that what we've been learning about, literally with vectors and these tables with numbers, like this idea of having a, vector 1, 2, 3, this can extend to like all sorts of things that you might not even understand is possible. It doesn't just have to be this idea of, having a vector 1, 2, 3, something like, I don't know, that. But, and it can be this, but this idea of a vector can be so much more, and that's the benefit of abstract vector spaces, which is what the topic of this unit is, okay? And this is actually the definition of what a vector space is, and it's a little bit long, but I'm going to kind of go through it and make sure it makes some sense here. So it's pretty general too. So it's saying that V is just a set, okay? And there's two operations that are going to be well defined on that set. So the operation of addition and scalar multiplication, and specifically scalar multiplication. Okay, that's important. That might seem really straightforward, and you probably have in your brains a certain thing, but that thing is not necessarily right. Okay, 2 plus 3, okay, is not necessarily 5 anymore. All right, 2 plus 3 can actually be 6. And we're actually going to do a problem where 2 plus 3 is 6, and it's really cool and really fun, and we'll come back to this idea. But the ideas of addition and multiplication are very different than what you think. It's just literally like this symbol is going to mean addition, but addition can be all sorts of different things. And then scalar multiplication is, this symbol where we just write two things next to each other. But again, don't necessarily think you know what it is. It can be more general than that, okay? And so basically, based on these two operations, all right, the vector space needs to satisfy all these different conditions, okay? And the C's and D's that you see in here, they are not necessarily coming from V, all right? V is the set of your vectors, but C and D are actually from something else called a field, okay? And so I'm going to actually add that right here. C and D are elements of F, where F is a field, okay? And fields, I'm actually going to define what a field is, but fields can be all sorts of different things that you know some of, and some you probably don't really know. They can be the real numbers. They can be the complex numbers. They could just be the integers. That's a field. There's some in ZP that is a field, and I will talk about what that is actually today. But these scalars are not necessarily in V. That's important to know, okay? So really, this definition up here, the best way to think about this definition is that it's saying, it's really defining a vector space over Rn, okay? Typically, we think in linear algebra of our vector spaces over the field of the reals, but they don't have to be. You can study harder linear algebra problems down the road where it's over the field of the complex numbers, and that's totally fine. But for right now, you can kind of think of the fields being just over Rn, okay? Or sorry, the vector spaces being over the field of Rn. And vector spaces just need to satisfy certain properties, okay? And So we have like this notion that if you have two vectors in the set, then the sum is in there. That commutativity should happen. That associativity with addition should happen. There is something called a zero vector in set. Basically, you add something to a vector and you get that original thing out, okay? For each vector, there is a negative of it where you can add them together, and again, it can be in a very abstract sense, and you get 0. Then here now we're getting into the scalars, C and D. So C and D are not necessarily from V. Okay, they can be, but they don't have to be. So anything from your field multiplied by the vectors in V, you can do distribution of the scalars, and you can also do distribution of the vectors. Okay, and then the scalars should be commutative. Okay, and there is a thing in the field that acts as a multiplicative identity, right? So it's a lot of different properties. I don't have them all memorized, and I've seen vector spaces for quite a long time, but you basically need to check all of these, or show one of them doesn't work to show something is not a vector space. But if you want to prove that something is a vector space, you do have to go through and prove all these properties, okay? And I have this other comment here. So I don't know how many of you know these words, but there's things that you study eventually in math called groups, or you might study something called a ring. Even more general, you might study something called a module. But there's these terms out there, and these all fit under, if you want to learn about them, go study something called abstract algebra, which is basically what it sounds like. It's taking algebra and studying the most abstract general rules associated with it. But in abstract algebra, you study these concepts and other ones too. And a lot of students confuse vector spaces with rings. And for any of you that will eventually take this class or do your own study on this, I'm going to say right now a vector space is not a ring. And this confused me when I learned these things, because I learned vector spaces and then I learned rings later, which is a very normal process to do that. And I felt like a vector space was like a ring, but they are not. There are some vector spaces that are rings. And if you want to know about this, I will happily explain it to you, and I can. But a vector space is not necessarily a ring. There is just some that are, but they're very weird cases, and they're not actually that useful. And a very, very quick explanation. Rings need to have well-defined multiplication on the set, like the set V. And there is actually no good sense for vector multiplication, right? We don't have the notion of what is V times some other vector. No, I don't want you to see. W, okay? We have things like dot products and stuff, but that's not vector multiplication, really. And so this is the thing that actually is confusing. And to be a ring, you need that multiplication, but we don't have it. So a lot of you can just ignore all that stuff I said because you don't need to care about that. But I know right now that some of you may have learned some of this already and or taking classes with it down the road. And I always got confused about that. So vector space, not a ring, only in very special cases. And those ones aren't really useful. Okay. So a field. I want to say a little more about a field here. So a field is another set, okay? And it does have to contain at least two elements. And there's operations plus and addition and multiplication here, all right? So, like for elements x and y in the field, x plus y and x times y are things in there, okay? And fields also have to satisfy a bunch of properties, okay? And so there's all sorts of fields in the world, and a lot of them. Rational numbers are actually a field. If you do things like, with the standard plus and minus that you're used to, or plus and multiplication that you're used to, you can do 1/2 times 2, and you get 1, and 1 is a rational number. So, that's like operation is in there. That's fine. Integers are a field. Complex numbers are a field. Rn is definitely a field. A clock is a field, okay? And so let me explain this one a bit. So a clock, I would personally write like this. I would write it Z12. Except one thing that's kind of weird in my clock is I would write my clock this way. I would write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 0. That's how I would write my clock. And in that sense, then it is a field, okay? So to be a field, you basically, there are things, finite fields, and this is an example of a finite field. If I take all the integers, from 0 up to 11, we would actually call that set Z12. That really is this thing Z12 here. So it's a set 0, 1, 2, all the way up to 11. And we call it Z12 because there's 12 things in that set. But you can actually think of this set of numbers as a field. And the things that are kind of weird is how you define like certain multiplications and stuff. So let's take kind of a nice one. Let's do 10. Let's do like 9 times, actually, I want to go smaller. 8 times 2, okay? So 8 times 2 is 16, okay? But there's no 16 in this set. But 16, the way you want to think about this is once you get to 11, then you start over counting again. So 16, what it would be, 12 is 0, and then 13 is 1, 14 is 2. If you're good at military time, this is basically connected to that. So this is 14, 15, 16. 16 is a 4, okay? So in this world, multiplication of 8 times 2 is actually 4, right? And if you follow those kind of rules, then you are actually going to be able to define this thing as a field. More generally, this is actually something called a quotient group. This thing is something called a quotient group. And group is another one of these things from abstract algebra. But when we write this z/nz, what that really is z with this little subscript n that I'm kind of using over here. So there's all sorts of things in the field of cryptography, which is like code breaking and stuff. And you use actually ZP a lot, where P is prime. This is a finite field where you can do things like Z2 is a finite field, and that is just binary numbers, basically 0 and 1. You can do Z3, which is another prime, 0, 1, and 2. And the multiplication is done like this way, where you kind of cycle back, once you hit. So here, 3 is like the 0, right? 4 would be a 1, 5 would be a 2, and then 6 would be a 0. So you get this kind of cyclic structure to these things. But those are some weirder ones. I mean, typically we're going to be thinking of our vector fields over Rn. So our scalars are just going to be normal real numbers, but they can be all sorts of things, okay? And they have to satisfy all these properties. So if we just think of these vector spaces, most of these are going to be, sorry, let me back up a second. So this is one of those finite fields. This is just the set again, 0, 1. And this is a vector space, but you have to take it over the field Z2. But the rest of these, okay, are well-defined vector spaces over normal field Rn, okay? This is basically a set of functions that map the real numbers to the real numbers. That is actually a vector space. Doing the same thing, but now map the naturals to the reals, actually also a vector space. There's this thing script P3, which is basically all the polynomials of order 3, where the coefficients here, the AIs, are basically just real numbers. That is a vector space. You can generalize this one to, we can do script P sub n, and it's just the nth order polynomials. And so n is natural numbers, right? You go like 0, 1, 2, 3, all the way up to n. But then the coefficients can be real numbers. Those polynomials, also a vector space. There's a very famous one called M 2 by 2. And it's literally just all the 2 by 2 matrices with, really, if you think about it over Rn, it'd be the real entries. But you could do it with other ones, too. There's things, this is something out of some field of math called graph theory. There's vector spaces there where they start to get even not numerical in the way that you think of it. This is, if you have G as a finite, simple, undirected graph, a spanning subgraph of G is a subgraph that contains all the vertices of G. The set of spanning subgraphs of G is actually a vector space, and it's over a finite field in that one. This is something out of topology, which is what I studied. And these are things called homology groups. Whoops, I just spelled it wrong. I worked with these for so long. Homology groups. This is actually a notation I'm going to explain to you at some point called a direct sum. And this one, in like here, is something called a tensor product. And it's very complicated to explain all this, and I won't explain this thing to you, but I will actually explain what a direct sum is at some point. But this is actually a vector space, this thing. And this is a very complicated vector space that I can't even really begin to explain. There's also a very simple vector space where you literally just take, and they call it the trivial space, and you just take like the zero vector. Like the zero vector in its own set is actually a vector space. There are tons and tons of vector spaces out there, almost too many to list down. And I like this joke, because it's kind of how I felt, because it felt like anything could be a vector space. And I'm not saying that's true, but it does feel like if you work hard enough, you might be able to craft vector spaces out of the most ridiculous things. I still don't think mayonnaise is going to be a vector space, but there's a lot of them. That's the point, okay? Very, very, very applicable to tons of areas of math. Really, the applied setting all the way to the pure setting in math, you can find these. Just to show a quick example here. So Z, or this ZP thing, which again is a finite field, one of those is a vector space over Z, but the other is not. And I strongly suggest you look at this definition of a vector space and try to pause the video and think about which one of these would be a vector space over this field. Again, this is where the C and D's are coming from. And it's a very quick answer, and I'm going to explain it right now if you haven't had a chance to think about it. Sorry. So the one that is going to be fine is actually Z. So Z over Z is a vector space. That one's good. Check. The issue with ZP is not, okay? In fact, any finite set V is not a vector space over an infinite set. Or let's use the proper word, over an infinite field. And the idea here is honestly linked to just, you can do it with like this one. So C is coming from Z, right? But you can take ZP, let's do 2, okay? There's only 2 things in this world. Oops, there's not that. These 2 things. This is what Z2 is. if you let C be 1, it's fine, right? If you let C equal 1, right, note that 1 times 0 is going to be 0, and 1 times 1, which is going to equal 1, and those two are fine. But this is the issue. If you let like C be anything beyond the elements of ZP, so do like 2, okay? 2 times 1, okay, is now equal to 2. Okay, this is like the normal multiplication here. And this thing is not an element of Z2. So C0 is not an element, is not an element of the vector space, right? Which is what it says right here needs to happen. So you can always come up with this if you pick some scalar that's beyond the size of P, basically. So any finite set V is not going to be a vector space over an infinite field. Now, actually, Z2 over Z2 is actually a perfectly fine finite vector space over a finite field. And there's other ones you can make up too, but this is true actually for finite sets over infinite fields. Okay, so these are all kind of corollaries. They follow from the definition of a vector space, and I think it's good to prove this, okay? So the other ones are all good to prove too, but I'm just going to pick one of them, kind of show you the feel of these. So if you have a vector space V, and U is a vector in V and C is a scalar, all right? So these are, again, coming from the field. Then all these different properties should hold. It says that if C times the vector U is equal to 0, then basically C equals 0 or U equals 0, right? Like the 0 vector. So we're going to prove D. So since we want to prove an OR statement, really the interesting one is the second one, right? Because we could say like basically do this in cases. Case 1, C equals 0. And then in this case, we're done, right? Case 2 is suppose C doesn't equal 0, right? Because that's going to be the interesting case. If C equals 0, you only have to show this or this holds, right? And if C equals 0, then we're done, right? And so I'm not really assuming the conclusion because I'm going to go through this case as well. So it's fine to do that kind of trick. So if C is not equal to 0, then 1 over C is well defined. And so basically the feel for these problems is you pick something over here and you just kind of, you're going to start with this and like work through these properties. And at this point too, we could also use any of these properties. Because really, like, you would prove everything in order, and we're at the bottom, so you could use these as well. And so what I'm going to start off with is actually this last one. So you could just say, like, V is a vector space, so 1, whoops, that's not the one I want. So U equals 1 times U. And what I'm basically going to do is show that U has to be 0, because that would do this, right? And so building off of this, we know that 1 over C times C, right, is 1. And then we have 1 over C, right, so that's fine to do. And then we can basically use a property from here, so basically the associativity of kind of the scalars and the vectors, so property 9. So this is property 9. We can regroup and do C, whoops, that's a C, CU. And then I know that what I have here is that CU equals 0. So really, I can just be like, okay, this is 1 over C times the 0 vector, right? And Then, so this is by basically our assumption. And then if I go by property B, okay, note that 1 over C times the 0 vector, right, is going to equal the 0 vector. So putting it all together, U equals the 0 vector, right? And that does it. And that proves both cases. So either if C times 0 equals, if C times 0 vector, oh my gosh, I did it again. C times U, the vector U, equals the 0 vector, then U equals the 0 vector, or C equals 0, the scalar. Different things, okay? Basically, this is saying, like, you know, what you're used to with a lot of algebra, how you can, like, factor things and, you know, set each factor equal to 0. All right. Another definition I just want to bring up, what you're going to see in this unit in general is a lot of the things that we have studied basically come back and just under different wording, okay? So I'm actually going to start here. So we saw the subspace of Rn way back in chapter 3, okay? And basically it was just defined as any collection S of vectors in Rn such that there is a 0 vector in that set. And if U and V are in there, then the sum is, so it's like closed under addition. And then if U is in S and C is a scalar, C times that vector U is also in the set. We can reword this just in the context of a vector space, okay? So a subset W of a vector space V is a subspace of V if W is itself a vector space with the same scalars addition and scalar multiplication as V. And in these vector spaces, these subspace ones, you still need these closure properties. Because it's a vector space, it has to have, like right here, property 4, it has to have this thing as 0 vector. So you'll notice that, you know, here there's 3 conditions and here there's only 2. But that's because set W is a vector space that, like, already basically implies 0 vector is part of W, right? It's contained in there. So you're going to see this a lot, where you've learned something that has to do with Rn, and all of a sudden we're going to just abstract it a bit and see that it applies to arbitrary vector spaces, you know, where maybe numbers aren't even a thing, basically. All right, so what I want to do here is just show one of these subspace problems. So I want to show that D, the set of all differentiable real-valued functions, is actually a subset of F, the set of all real-valued functions, okay? You know, we know that some real-valued functions are not, you can't take the derivative of them. So these two things are actually vector spaces, real-valued functions, and differentiable real-valued functions. And so we should be able to go through a proof here and show that actually this set D is a subspace, an abstract vector space subspace of F, okay? And I don't have time in this video to do that, but I do want to do it still. So I'm going to do it in another video. But in that other one, I'm just going to hop into it and basically show that this space D is actually contained inside of F, the set of all real-valued functions.